Hello, I am Theodoros Tsourdinis, and I will present you our demo for the paper entitled AI-driven service-aware real-time slicing for beyond 5G networks. In this work, we are dealing with a real-time allocation of slices for the 5G network based on the type of service that we recognize as being executed on the top of the network. The figure on top summarizes the framework's architecture, showing the deployment of the service-based 5G network, the introduced AI/ML unit, and the internet applications that the end users interact with. It's cloud-native 5G network fully deployed on Kubernetes. The core network follows control and user separation architecture, while the front-haul radio access network follows a disaggregation architecture that incorporates a near real-time flexible controller. We generate traffic between 3 containerized applications and 3 commercial UIs. The applications that were used are a video streaming WebRTC application, a voice over IP application, and a simple web server. The setup is based on a real testbed, Nikos testbed, as the availability of Nikos wireless devices suits our experimentation needs for evaluating our solution. In this video demo, we will showcase the various technologies that we use from the Kubernetes ecosystem, such as Docker containers that running in the open-air interface network instances, the AI unit that utilizes PySark for live traffic capture and TensorFlow for the employment of the LSTM neural network. We will also present a distributed online training mechanism. This mechanism employs Kubeflow pipeline. So we parse the data from the MySQL database, we will process the data, and we train our LSTM model across the Kubernetes nodes. When the training finishes, the updated model is stored as an HDF5 file in the network file system persistent volume, and then can be used by the predictor service to enforce slice allocation depending on the type of application in the network via the flexion controller. So now let's move on to the demo. Through the control plane Kubernetes node, master node, we deploy all the appropriate pods containers with the help of a bash script. More specifically, we deploy the following pods with their respective functions. For the core network that follows a control user plane separation, we deploy a Cassandra-based database, a home subscriber service, a mobility management entity, a control plane, and the respective user plane service, SPGWU and CPods. For the front haul that follows a disaggregation radio access network, we deploy CU/DU components and the flexer controller. And for the internet applications, we use the WebRTC video streaming, the voice over IP SIP server, and the Nginx web server. For the AI/ML unit, the app-aware predictor container is running inside the SPGWU pod. So after all the pods are running, we monitor the logs of the app-aware predictor as well as the logs of the flexion controller. The app-aware predictor service is waiting for all the UIs to connect to the network so it can then initialize the slices via the flexion API. Therefore, we connect 3 UIs to the network and immediately see the initialization of the downlink slices with the corresponding percentages of the resource blocks in the Flexrun logs. As there is no interaction with the application, the available resource blocks are shared to them among the UIs equally. Then to generate traffic between the end users and applications, we apply some traffic scenarios in the UI terminals with the help of bash scripts. Following this, we make sure that all 3 UIs interact with all 3 applications by watching the video streaming through the WebRTC protocol and the SIP and the Nginx logs. In the meantime, the app-aware predictor is capturing all the packets between the end users and services in real time and performs traffic classification and makes prediction about future interactions between end users and application by utilizing a shared pre-trained LSTM model. We monitor the entire operation of the app-aware service through the logs, which shows us the input window, the predictions for the next 5 seconds, and the slicing policy. The input window is the input structure for the LSTM model. It includes the 30 most recent interactions between end users and applications. Predictions are each output value that represents the predicted network traffic of a specific UI app combination. Slicing policies are the decisions for making resource block distribution among the UIs. As a reference example for the operation of the ML framework, we showcase the moment when the service makes the prediction for the interaction between the third UE and the WebRTC application. At the same time, as the prediction is made, more resource blocks are provided in the UE3. Then, as we expected, the UE3 interacts with the WebRTC app, experiencing high quality of experience. As we can see, the prediction and the slice reconfiguration to the network happens continuously for this type of interaction. Then we showcase a continuous delivery of our ML framework by utilizing Kubeflow pipeline. First, we deploy a MySQL 7 packet sniffer container. Packet sniffer live captures all traffic between the end users and applications and stores the summary of the packets in the MySQL database. As you can see, the most recent traffic data is continuously getting stored into the database. Our pipeline is described in a Python script, which after compiling it, it produces a YAML manifest, which we upload to Kubeflow pipeline service in order to run the pipeline. There we see the Kubeflow user interface, which gives us the opportunity to run our AI pipeline in a user-friendly way. In this form, we submit the name of the pipeline and we upload the YAML manifest. After uploading it, we can see all the pipeline steps in a cycle graph. The steps are data parser, data preprocessing, and the last step is the training step. After exploring the running options, we simply run the pipeline. The first two steps finished already, so then we monitor the logs of each step in the Kubeflow UI. And next, we track the training process. So when the training finishes, the updated model is stored as an HDF5 file in the network file system, persistent volume, and then can be used by the application-aware predictor service as it mounts the same volume as a training component. The pipeline can be triggered by the predictor service periodically with a timer, or each time the predicted data is less accurate than a predefined threshold. So this was it. Thank you for watching. The video demo is also uploaded on YouTube. There is also a GitHub repository for easy reproducibility of the experiments. Do you have any questions?